weighted average. So you put composition of, let's say, gallium arsenide, or in this case, this is the lattice constant of gallium arsenide, and X will be the molar composition of gallium. This will be indium arsenide here, and then 1 minus X will be the molar composition of indium. So that's how you can calculate the lattice constant. Again, the idea here is to match to the substrate. Okay, when you don't have a substrate available for such a terminate compound, okay, you don't typically, you cannot get anything you want. But indium phosphide wafers are available. So that's the whole idea here is you are trying to match your composition to lattice constant of your composition to an available substrate. Okay, again, to put into perspective, here we are talking about epitaxial growth. We are growing a material, thin film, a single crystalline on a substrate, and of course, particularly here, we are talking about heteroepitaxy, which means we are growing a material on a different substrate. Okay, and then you can do the same for nitride-based semiconductors. Again, probably mentioned that gallium nitride and aluminum nitride, gallium nitride and their composition, they don't have a substrate. Okay? You cannot buy gallium nitride wafer. You cannot grow it. There are smaller wafers, expensive. So what people develop is, the growing gallium nitride on sapphire or silicon carbide. And if you want to grow other composition of gallium, indium, and aluminum, so you can grow something like this aluminum indium nitride or gallium indium nitride, then you can select the composition to have a best lattice constant match to the substrate, whatever you are growing. Okay. So the idea or the advantage of epitaxy is you can either have a built-in strain. When you don't have perfect lattice match, there will be strain, as we'll talk about in a moment, and that may bring some additional benefit. Okay, strained materials, especially in the silicon germanium case, improve the mobility, so you can have better devices. That's one benefit. Same for gallium nitride or nitride-based devices. When you strain them, there's an induced electric polarization or electric field in the material which pushes the electrons to a channel, so you will get high carrier density in the 2D electron gas channel. So that's why you have a very good transistors for gallium nitride. You don't have to introduce dopants to increase the electron concentration. Built-in strain, their nitride-based materials are non-centrosymmetric, so there is a built-in piezoelectric field within them. It pushes electrons in a certain direction, and you can get a high sheet carrier concentration, electron concentration for high current. The second reason is, as I just explained, when you don't have an available substrate, you can grow on a different substrate. There may be lattice mismatch. You can develop methods, as I will show, but you can get large wafers to be able to produce devices. That's how the gallium nitride HEMT devices, high electron mobility transistor devices, that are used for all amplifiers in right now cell towers and everywhere. Okay, they are much more efficient compared to gallium arsenide at high frequencies. So everything is replaced with gallium nitride, and that's how they are made. You cannot have gallium nitride wafer. Gallium nitride is grown on typically sapphire. Okay. So that's what there are two cases, of course. One's in the beginning there are two cases. Either you have lattice match perfectly, then which you don't have to worry about anything. Then when you have lattice mismatch, meaning that this is overlayer, that's what you want to deposit, and that's epitaxial layer you grow on the substrate. If your overlayer has larger lattice constant than the substrate layer, you can have two cases. One is you can grow as it is. Okay, that's incoherent growth. In this case, you see atoms are not perfectly aligned, so you will end up at some dislocation densities at the interface, okay? Or if the overlayer has smaller lattice constant, it will be basically the same. You will have less bonds, still it may result in some interface defects. Okay, so this is incoherent growth. The opposite case would be a coherent growth. Yes, your overlayer has larger lattice constant, but when you grow, it feels a strain, so the atoms push themselves to match or to align themselves with the atoms of the substrate, as you see here. That will result in a built-in strain on the overlayer, of course also on the surface of the substrate, but more so in the overlayer, the epitaxial layer. And if you grow a thick material, eventually it will result in strain relaxation and some defects. But if you can accommodate, then you will have a perfect layer. So as long as it's below a critical thickness, and this is coherent strained growth. Okay. And as I said, up to critical thickness, we can grow it. And critical thicknesses. This is a very crude equation. I mean, it strongly depends on the materials. So the AS is the substrate lattice constant, and the epsilon here, defined here, is the mismatch. Okay, so AS minus AL over L. So if it's approximately this value, you can, or the overlayer may accommodate the strain, so you can grow without any defects. But below that, beyond that, you will start having defects. As you see here, I mean at the top you may get cracks and dislocation baskets. So this is a very good picture of it. This is sapphire alumina Al2O3. That's sapphire. So gallium nitride is grown. You see at the interface because they have lattice mismatch. Some of them, are some of those defects propagated all the way to the surface, but some just stop at the lower thicknesses. But there are ways to reduce them. There is a lateral overgrowth technique, and this is now used in the industry to grow gallium nitride and combination of nitride semiconductors, aluminum gallium nitride, indium gallium nitride, etc. And this is how you see them from the top. Those are dislocation densities. Again, missing atoms, missing layer of atoms, etc. I will quickly skip those things. Strain tensor. What's strain tensor? It's basically how much pressure force you apply in because of the mismatch. Atoms will attract each other to trying to align. So there, of course, when you look at it, there will be parallel to the surface, right? Because it's in 2 dimension. Also, there will be a strain in the perpendicular direction, right? So sometimes the coherently strained crystals are pseudomorphic, not really morphic. Morphic means they match. This pseudomorphic because by applying or by feeling some strain, they force themselves to match to the substrate and have the same lattice constant up to a certain thickness. Beyond this, it may not be. They cannot have the strain and just crack. So the perpendicular mismatch is given by this of the strain, and that there's a Poisson ratio that relates to the strain parallel to the surface and vertical to the vertical direction. It's called Poisson ratio. I'll skip those things to material science. Now we were talking about the epitaxial methods. One method is called liquid phase epitaxy. So in this case, we melt the material that we want to grow and then move the substrates on top of it. It's not used much in the industry anymore. This is a typical LPE machine. MBE is commonly used or very versatile and very useful research tool, molecular beam epitaxy. It has low throughput, so you cannot grow large amount of wafers. You can grow a couple of wafers, but you can precisely control the thickness and of the material you grow, the thin film, and also the composition. So it is performed under very, very high vacuum, and it's kind of a solid phase epitaxy, meaning that you evaporate those material through effusion samples, effusion cells here. As you say here, as you see here, you put the material you want to deposit, you heat it, and you can have many of them, so that you can have an alloy with the desired composition. Okay, that's dopant, gallium, arsenic, aluminum, dopant. You can deposit aluminum gallium arsenide with varying composition, and you can also introduce dopant atoms, and you evaporate them at very, very high vacuum. Those molecules reach to wafer and get deposited. So, and the deposition rate is extremely low, so you can get a very smooth surface with extremely well, precisely controlled thicknesses. You see here, this is so-called super lattice. So there are gallium arsenide and aluminum gallium arsenide layers. I think the number of layers are given somewhere. We had 48 or something like that. I forget. So you see that those are 4 monolayers, so 4 atom thick, and it's precisely controlled. And such structures are used especially in photonic applications. You can have a so-called Bragg reflector. You can have multiple layers, and the laser is perfectly reflected at certain frequencies. So you can make a gain, medium, etc. You can have smaller number of layers for high performance FETs, field effect transistors, etc. Again, it's extremely flexible. You can deposit almost anything, and you can control precisely the thickness, but it's very slow and very expensive to set up something like that. But not very convenient for large scale production. CVD, we talked about that, I believe. The chemical vapor deposition. There are two different limiting cases for CVD. This is a particular case for homoepitaxy of silicon. So we grow silicon on silicon using silicon chloride, and that allows. It could be either atmospheric pressure or low pressure, and also under plasma. So that in this case it's called plasma enhanced chemical vapor deposition. Again, it allows growing silicon on silicon with different characteristics. You can dope this second layer whatever you want to dope. Okay, that's the advantage of silicon CVD. MOCVD, this is again very, very common, widely used method for gallium nitride technology nowadays. All your LED lights are produced, or the material for LED lights, blue lasers, etc., are produced using MOCVD. So this is metal organic chemical vapor deposition. Metal organic because the metal atoms like gallium and aluminum are carried by organic molecules like CH3, what's that, 2-methyl or methyl groups. So they are carried, if you remember, the AI, the atomic layer deposition is very similar to that, but here it's not self-limiting process, so you have to control the thickness by the flow rate. So it's a chemical reaction, obviously. It's not like we should differentiate it from the physical deposition methods. This TMI, 3-methyl indium, it could be also 3-methyl gallium, 3-methyl aluminum, is carried by those three methylene molecules, and they react on the surface to leave the whatever they carry, in this case indium, on the surface, and then remove the CH4 methane. The gases, so there are carrier gases. This is how it works. Typically hydrogen 82. It goes through bubbling bubbling chambers here. So those bubbling attracts the whatever you want to deposit. This TMA means 3-methyl aluminum, 3-methyl gallium, 3-methyl indium. So as hydrogen goes through, binds to whatever you have here, and then carries them through the delivery, and they react on the surface because of the heat, typically to increase the reaction rate. So the fundamental process here is chemical, to have a reaction on the surface to deposit whatever you want to deposit. This, advantages, you can grow many different materials with quite high quality. One disadvantage is probably it uses some toxic gases and complex chemistry, especially for certain materials, like this is arsenite or arsine, this is phosphine. Those are toxic gases, but you don't have to use them for all materials. Again, this is, especially for gallium nitride, this is the major method of production. As I said, briefly mentioned, when you have this lattice mismatch between the substrate and the overlayer, you will end up with some dislocations, at least beyond the critical thickness. So people develop some interesting techniques. One of them is epitaxial lateral overgrowth. So a thin layer is grown and then etched, and with so you have this one, and then you etch. This doesn't look very good. And then you put some sort of masking layer, okay, and then you grow over this masking layer. So let's say this is what you want to grow. The pictures look very good. This is no deposition oxide, but what is oxide is not shown. I presume this is oxide. So this is the thin material. You deposit it first. Let's say it's thin gallium nitride, and you can etch it. You put oxide, and then you grow. When you start growing, as you see here, you first will have some pyramid-like structures, but then it will grow over this layer, oxide, the mask layer, and laterally and vertically. So you will cover over this. The advantage is whatever the dislocation you have here will not go in this direction. So this mask layer will block the dislocations. So you can make those larger to grow laterally, large area, and block most of the dislocation. So you will end up with higher quality of lateral overgrowth, epitaxial lateral overgrowth, or sometimes lateral epitaxial overgrowth to make it real. But it's a good trick people have developed for nitride technology. Coming back to stress, when you deposit metals on thin metal films on thin dielectrics, you may end up with either tensile or compressive stress. So with the tensile, you have a larger atomic distance for the overlayer, so it will push the atoms. So you will end up with upward bending, and for compressive stress, you will have lower negative bending. As you see here, that silicon dioxide aluminum cantilevers. So you can take advantage of that to bend materials in the desired direction. Okay? So by selecting what you deposit on the what, you can bend in either direction, and use those cantilevers for various applications. They could be sensors and other MEMS, micro electromechanical systems. Of course, one thing that you kind of missed here, so you may have stress or strain for two reasons. One is intrinsically your atomic distance, that's the lattice constant, is different for different materials. But other very important point that you have to keep in your mind, the thermal expansion coefficient. If you have two materials, and especially they have different thermal expansion coefficients. One expands with temperature more than the other, and if your process or your application requires high temperature, then you may end up with this extrinsic stress, which may result in film failures. So you have to pay attention to thermal expansion coefficient of your materials and devices. And stress could be measured using stress measurement techniques. There are tools for that, which I will skip. Perfect. Any question for this thin film chapter? So we covered, just to sum it up, there are two major types. One is physical vapor deposition, PVD. The other one is chemical vapor deposition, CVD. In the physical method, we simply evaporate and get the material deposit on the substrate. There is no chemical reaction. We evaporate the charge, whatever you want to deposit, and gets deposited, absorbed on the surface. For the chemical vapor deposition, there is a chemical reaction going on the surface. So you carry whatever you want to deposit, probably another molecule is attached, CH3 for example, and then it reacts with the surface, then leave the molecule or atom you want to deposit, and then there is a byproduct out of that. And there are typically you need a high temperature for that to increase the chemical rate, etc. And epitaxial growth is growing materials on different substrates, etc. So those are the fundamental things about this chapter. Okay. So next chapter is about the metrology, so different measurement techniques. Of course, now we have learned so far the patterning. So you will, spin resist and then transfer your pattern using mask, etc. Now you have fine features, right? You want to see. Let's say after that, if your pattern transfer is successful, you either deposit or etch, just like you did, and then you check it again. You did, right? You measure the thickness and the critical dimension, CD, if they are within your tolerances, your process requirements. So all of those things are related to metrology, which is a very important part of the microfabrication process. So the simplest, easiest, and most common method is of course the optical microscopy. You can look at the minor microscope, take pictures, and even movies. If you have a moving part on your device, that's if your devices are large enough to be able to resolve with optical wavelengths, then you are good to go. So optical microscopes are the most commonly used metrology tools. I'm pretty sure you are familiar with the parts of a microscope. So there's a head, eyepiece, coarse focus, fine focus. You put your sample here. There's a stage. There are different objectives with different magnification powers. There's typically another 2x or 5x eyepiece magnification here. This could be from 5 to 100x or so. And there are illumination here, a lamp. There's a blade here to control the light, as you'll see later on. That's pretty much it. Of course, the limit of optical microscope is the optical limit. So, the visible lights are between 400 to, let's say, 700 nanometers. So you cannot resolve anything in this range, or smaller than this range. We cannot resolve anything, let's say 400. So that's half a micron or so. It's very difficult. And remember, the optical resolution limit is typically lambda over 2. So if you can see 500 nanometers, 250 is the resolving power, but even that is very difficult with a typical lens system. There are sophisticated microscopy systems, so many of them. I will cover some that could benefit your research or applications. Fluorescent microscopy is commonly used mostly by chemists and biologists, So that some materials are fluorescent, meaning that when you excite them, when you send light, you excite electrons to higher energy levels, and those electrons go down to lower energy levels later on. Of course, this energy difference is released as a photon, typically less than the energy you excite them. So you can look at those photons and then see what's in there. Sometimes you can add those materials, especially biologists do it a lot. There are molecules with distinct fluorescent wavelengths, so you can introduce them into a specimen. You can attach them, nanoparticles or cells or some other molecules, and you can track them, because when you light, they will fluoresce. You can see them in dark, so you know where those molecules end up. But you can use them also in semiconductor testing. As you see here, this is a semiconductor circuit, and you can see there is something here. Okay. So the way it works is you excite light. So this is a laser. It could be 532 nanometer. That's green laser. I think that's what's shown here. It could be something 700 also. People use that. And it goes down to the specimen, excites electrons or dye. Well, dye means basically the mechanism is to say it's a special molecule with different metastable levels. You excite electrons to higher energy, and they go back. They emit light, and you collect the light. There's a mirror here which lets only the fluorescent light go through, not the excitation light. A differential interference contrast microscopy is an interesting method. So when you have quasi three-dimensional, not so planar specimens, like for example cells or microorganisms, you would like to see the thickness or get some information about thickness. So people develop this one. Regular microscopes cannot deliver such a image. So the way it works is there's a so-called Wollstoned prism, which separates the two polarization, X polarization or Y polarization. So now you have two different optical paths for two different polarizations. Okay, they go through and they interact with the matter in a different way. Okay, and then they are combined again to form a image, and that allows you to see thickness or the optical path difference, which means kind of a depth sense. So that allows you to see in more 3D sense your specimen. Again, it's very convenient for living organisms, but also could be used for nanoparticles or small structures like that you want to see in 3D. Bright and dark field microscope is commonly used. We have this capability. Almost most microscopes may have this. So in the bright field microscope, the light goes through the specimen. So this is your specimen, either in reflection or in transmission mode. Here it's shown in reflection. You see it goes through your specimen. So you see if you have boundaries for any reason, let's say if you have photoresist, you will have photoresist, you will see the photoresist boundaries. very faintly, but when you use in the dark field mode, so you put a shutter in front of your light, so the light will not go through directly to your specimen, but mostly from the edge. You see, this light will go through your specimen from the sides. So, and you will see most of the scattered light rather than the transmitted light. So that allows you to see the boundaries. It's very convenient to check after you're developing to see if your sidewalls are good in your photoresist. So I would recommend you to check it if you haven't already. Use both bright field microscopy and dark field mode to check the sidewalls. You will get a better understanding how your sidewalls are after developing the photoresist. Yeah.
So light field uses transmitted light and dark field uses.
It's mostly scattered through the, you see this here is scattered. It's not directly going through the specimen, but this goes here, scattered, and some of them end up in the objective. Okay, it's from the sidewall. So you can see better, you can see the effects of the sidewall better. We talked about scanning electron microscope in earlier many times in EV lithography, etc. So it's basically acceleration of electrons due to de Broglie theorem. Any moving particle has an associated wave, and that is given by h over p. H is the Planck's constant, p is the momentum, which is m times v. So if your m is very small, like an electron, you may still have a large v, and then you can get very small lambda. And then if you put the numbers, you can get that typical lambda is on the order of less than an angstrom or on the order of angstrom. So angstrom is, of course, 0.1 angstrom is almost exactly the hydrogen atom radius. So you can resolve almost that small pieces. We talked about that before. And we can get very fine features or pictures of fine features, very high resolution. You can resolve almost under the nanometer scale. It says 5 nanometer, but you can see easily nanometer scale, and you get very beautiful pictures. We have a CM, and it's a very good skill if you learn how to use it. You can get images of your features, very nice images. And a variation of that is still kind of scanning tunnel microscopy. Scanning tunnel microscopy is based on quantum effect. So when you have two materials very close to each other, electrons can jump through this gap to the other material. It's a quantum effect, tunnel effect. Although there is no connecting wire, you can still have a current. Okay, there is a finite probability of electron to jump over a potential barrier. So when you implement it in a way like this, a tip, very, very fine tip, and if you scan over a surface, if you apply bias between those two electrodes, two parts, one to tip and the other one is the sample. Of course, the sample could be grounded, and you apply bias on the tip, and electrons will jump from tip to the substrate. And if they are closer, you will get a higher current. If they, if there is a dip here, a trench or something, there will be a longer distance, and the tunneling probability will increase with this distance. So you will have lower current, as you see here. Another method would be you can set the current to a limit, current to a constant mode, and feedback loop will change the height of the distance between the tip and the substrate, trying to keep the current constant. In either way, you can get an information about the distance between your tip and the surface. So that allows getting a surface profile like this, right? Almost at atomic level, right? So those are individual atoms measured by STM, scanning tunnel microscope. Of course, there is one problem here. If you have atoms with different electronegativity, meaning different conductivities, okay? Electronegativity means how efficiently an atom can attract electrons. So let's say here, I think this is an oxygen, it's not very electronegative. So it behaves like, or you see it as if there is a hole here. Although there's an atom here, but this is an oxygen atom or another atom on the surface with different conductivity or electronegativity. So that may result in some false imaging, false information, but if you know about that, that's another big problem. You can resolve atoms, okay? So, you can get, this is called coral, and it's even possible to pick those atoms by applying bias and place them the way you want. And I think I showed that picture a long time ago. IBM managed to write IBM letters using individual atoms. TEM, also very commonly used research tool, transmission electron microscopy. So it's very similar to SEM. Electrons are accelerated. So this is the electron beam, and the lenses, etc. Etc. All the beam shaping tools, and then you put your specimen somewhere in the middle, not at the bottom like the SEM case. And electrons go through your specimen, not reflected back like the SEM case. And that results in two types of interactions, or you can get two types of information. This is a picture of an SEM, TEM, typical TEM, very similar to the SEM. So this is electron, where the electron gun is accelerated. There are some electron optics here, the lenses, etc. You can put your sample here. It's an old one, so I presume that it's a fluorescent screen here that I will explain. No, new ones don't have something like that. So this is replaced with electronic version. So coming back to those two types of information. One is electrons, when go through your sample, they will be absorbed or scattered by your atoms. So you will get an image like that. Dark field means electrons either scattered or absorbed. Bright field means electrons can go through easily. So you can get atomic level picture of your sample. See, those are individual atomic layers, okay? And the distance, as you see here, 2 angstrom, 0.2 nanometer. It's extremely small. So that it's also called HR, high resolution TM. It allows you to see your sample if it's good crystal. Okay, so if you have something like that, it shows very good crystallinity. You can see, especially if you work with nanomaterials like carbon nanotubes or nanotubes, nanowires, you can see if they are single crystalline or what does it look like, the structure. So very, very convenient. Okay, this is based on intensity of transmitted electrons. The second information is, as you see here, this is the diffraction of electrons by the atoms. So when, if you remember from the light experiments, when light goes through this double slit, it diffracts, right? You see the diffraction pattern. Very similar to that. Electrons go through several atoms, so they behave like those slits in your optical experiments. So it produces a complex diffraction pattern like you see here. Of course, this pattern will depend on how the atoms are placed in your sample. So by measuring the distance and angle between them, how those bright fields are aligned, you can get the crystal structure of your sample. It's an extremely powerful tool. I mean, it's as if you are kind of mapping the 3D structure in your sample. There are software automatically determines which point corresponds to what in the crystal's orientation, and tells you, okay, this is, let's say, silicon, and this is the direction of 1110 or whatever. It's shown here. It's a 1012 direction. It's obviously a hexagonal structure. That's why we have 4 numbers here instead of 3. but it tells you the direction and material, so it's extremely convenient too. Very, very useful. So, anyways, this in the old TMs, this bottom here, there is a fluorescent screen. Literally fluorescent means, when electrons hit there, it just fluoresces and you see the structure. But in new ones, they put detectors here, so no more this old screen. You see everything in modern. There are detectors, sensors, or cameras, more precisely. Take the diffraction pattern and show you on the screen, and you can manipulate or analyze. So the column is shorter or lower in modern TMs. And typically TM and SEM techniques or tools are combined now. If you buy something, you can use it as a TM plus SEM at the same time. AFM is kind of similar to the STM, okay, but it's simpler and easier to use. So typically, what I use an example: if you go into a room, in the night time when your lights are off, how do you find your way? Right? How do you recognize what's where? What do you do?
Or get used to the darkness?
No, I mean until then, let's say. What do? How do you find your way? Yeah, you touch, right? You feel around. You touch. That's very basic stuff. So that's what we do. At the very small scale, there is no light practically. I mean, light wavelengths are so large you don't see them. So we touch to feel what's going around, or what's around, right? So this is a cantilever with a very, very sharp tip at the end. So we move it on the surface as there is something. See here, this is how it works. So the tip basically feels what's on the surface. As you move, it will be deflected, and you can measure the deflection through a laser interferometer very precisely, and then measure the topology of the surface or morphology, like something like this. There are typically two ways, two modes. One is static mode, you just drag it and then measure, and the dynamic mode, it oscillates and then measures. That dynamic mode gives reduces the noise. But either way, you can scan the surface and get quite accurate and very, very high resolution images. You see here, this is graphene. So this is 1.4 angstrom between atoms. So those, the bright yellow shows actually the carbon bonds between carbon atoms. That's so impressive. We can see almost the atoms using a mechanical tip, right? No electronics. No very sophisticated techniques are involved. Very simple, a tip, just scan over it, and you simply monitor how much it's deflected, and you can monitor, you can image the atoms. There's another one, relatively larger features, but you can get quite a good 3D map. This is a nanowire-based transistor, source, drain, 2 gates. Again, see, it's under the nanometer. You can get a 3D map or 3D image of a transistor. A little bit cruder version of this is a surface profilometer. We had something like that. I don't know if it still works.
Yeah, still works. It still works.
Right. So, I mean, it's the oldest one, as you see. I mean, even the image or the way it looks is old, right? So it's basically the same thing. There's a tip, and you just scan over a distance, and then as the tip moves, it measures. I think it's using a piezoelectric sensor, not a complex one like the FM. And then you can get typically for on the line, so it's kind of a 2-dimensional measurement in a way, and it aligns itself. Have you used that tool in the past?
Yeah.
So you know how it works. The resolution is okay, but it's not as good as the FM. One thing related to both AFM and surface profilometer is the lateral or the width of the trenches or lateral separation between features. So as you see here, if you have such vertical patterns, they could be metal strips or dielectric or whatever. Or if you scan after, let's say, photoresist, you may have something like this. And if they are separated enough, your tip will go over and down quite accurately and giving you reasonable result. But if they are very close, so your tip may not go into the bottom of this Peter trench, and it may give you erroneous results. You may not accurately measure the height or even the separation. So you have to be careful about that. When you measure, is it within the limits of or capabilities of your measurement tool? For this case, you may consider measurement using, I don't know, ICM or AFM maybe. Again, it depends on the depth and thickness for the separation. And one thing is, of course, if you have very large area and so if two dimensions or directions are in different scales, then you may need to use different methods for those two. What I mean is, if you have large area, if and then there's this very small feature at one point, and if you want to measure both of them, there's probably no good tool to measure both of them. You can resolve this probably using AFM, but then you cannot scan a very large area. Okay. Then there are optical techniques for the same, the thickness measurements or height measurements. Ellipsometry is most commonly used one. It's good to measure the dielectric film thicknesses. Almost all clean rooms have one version of it. You can measure the multiple layers of dielectrics. You can measure and also match it to the model. They typically have different models, and tells you, what is the thickness of the first layer, second layer, etc. And to be able to do that, of course, we need multiple parameters. If you have multiple equations, or if you have multiple unknowns, you need multiple equations. For multiple equations, you have to change different parameters. So for ellipsometry, typically you measure the reflection by scanning angle. That allows you to measure one thing, the angle. Then, as a second parameter to increase the number of equations, you can change the wavelength, that's the color of the light. So you can change both the color, the wavelength, and the angle, and you'll have more equations to solve more unknowns. Reflectometry is simply to reflect the shining light and measuring it back, and that allows you to measure the thicknesses. X-ray reflections using X-ray. But this is a simple ellipsometry tool that is commonly used for thin film measurements. Then there are electrical measurements. I'll not be able to finish it. Let me stop here because we started electrical measurements, so instead of cutting in the middle. So we'll continue and finish next time. Any question?
So were you able to find the file for the root owner?
I'm sorry?
Were you able to find the file for the
Yeah, I will check it. I'm sorry, it's my mistake again. I didn't check if, I presume this file is still available. If not, I will change everything and put it back. So don't worry about it. I'll send you an announcement for it. I apologize for it.
Next week, we started it early and we're able
Oh, yeah,
to
you
address
guys
it.
remember that.
Yeah, nothing.